All right, let's look at topic 12, direct substitution and the properties, some properties of the limits. Now, what is true if the limit as x approaches c of f of x is equal to f of c? Well, if that's true, then that means that the function is continuous at c. And we'll talk more about the definition of continuity later. And that might not seem like a big deal. That might be like, all right, I mean, what good does that do me? Well, it means that the function value is continuous at this point. So the limit of the function, when you're approaching, if you're wanting to know the limit of the function, you approach from the right and from the left, it's the same thing as the function value. So if a question is asking you about a limit, find the limit, then you can just find the function's value at that point. So now, do you have to say, well, do I have to draw the graph to see if it's continuous? Well, hopefully you'll see that. You'll know that in your head. For example, this first one, I mean, if you think about the function 3x squared plus 5, it's a polynomial. Polynomials are always continuous. So what you're going to do is you're just basically going to find f of 2. And so you're going to do that by plugging this 2 into the value of x, hence being called direct substitution. So I'm going to take 3 times 2 squared, it's an ugly 3. So 3 times 2 squared plus 5, and I'm going to work that out, and I get 4, 12 plus 5, and so I get for a final answer that this limit is equal to 17. Now, I know that this, you're like, do you have to show work because I could just do this in my head? No, on the notes I'm showing some work. But if I have a square root, again, direct sub, I'm going to put that 1 in for the x. So I have the square root of 5 times 1 minus 2. 5 times 1, 5 minus 2, and that is going to be the square root of 3. Now you're probably saying, well, gosh, how do people miss these? I mean, how are they missing this if you're just plugging in? Well, it could be a memory issue. If I throw trig in there, the direct substitution part is easy. If you put in 3 pi over 4 for x, that's the easy part. But can you remember from the unit circle what the cosine of 3 pi over 4 is? So you have to think the pi over 4s. Those were the square root 2 over 2. 3 pi over 4 is in quadrant 2. So I get a negative square root 2 over 2. So yes, you have to remember your trig. What is the sine of 0 over 0 plus 5? That's the direct substitution part. The sine of 0 is 0. I have 0 over 5. Is that an okay number? Yes, 0 over a number other than 0 is just simply 0. Now, what happens on the next one? Let's do the next. You're probably thinking, oh gosh, how is this hard? Direct substitution will always work. Well, let's look at the next one. If I plug in 0, that's the square root of 4 minus 2 over 0, not 2, over 0. So that's 2 over minus 2, that equals 0 over 0. Yikes. What does that mean? Well, the thing of it is I'm not going to do these today. We'll deal with this another day. When you get 0 over 0, you need to know that this is called the indeterminate form. Indeterminate form does not mean the answer is 0. It does not mean the answer is undefined. It means you have to do more. You have to do more because you cannot determine what the answer is in this form. So we will deal with that another day, but I just wanted to show you example of, well, when does direct sub not work? Is there a case where direct sub is not working? And so I want to say yes, that when you get 0 over 0. Let's look at the next one. When I plug in -2 direct sub, I get -2 over 0. What does that mean the limit is? Well, right now, we're going to look at these more closely as well. But we can say this one, the limit is undefined, right? I mean, or in other words, this 2 over 0 is undefined, which is going to mean the limit does not exist. Now, we're going to be, okay, so this piece is undefined, but we say limits do not exist. When we're going to explore these later, we're going to talk about a little more specific of what if we want to put some infinities in there, but again, we'll do this another day. So what we figured out is that direct substitution works if you get anything but 0 over 0, or I'm going to put non-zero, like a number like this one, -2 over 0. Those are the times where direct substitution, you're going to have to do something else to get those limits. All right, let's look at these. Oh, piece functions, piecewise functions. Now, granted, I could graph these whole things, but as we go through calculus, remember these are most likely going to be on multiple choice. You want to do these in the fastest way possible. So let's just think of a piecewise function. And what you're thinking of is you have, you're graphing one piece, okay, up until you get to a value. So in this case, like 1, and I'm not even drawing that graph accurately because it's linear, but, and then you might have an open circle or closed circle, and then you kind of attach the next one to it. So from 1 to 3, you're graphing something else. And so the graph, might look like this. Sometimes they end up being split like that, whereas sometimes, remember, you have an open circle, but then that next one closes it in. Well, look at those two graphs. Remember when I asked you about a limit, the limit as x approaches 1, I'm asking, does the left limit equal the right limit? So in this case, the answer would be no. At 1, the limit would not exist, whereas this guy, the limit would exist. So to make this very, very quick, I'm just going to take the limit from the left and the limit from the right and see if those two things are equal. And again, on this first example, I'm going to write it out so you can see it written out, but the second and third, I'm going to do really, really kind of shorthand notation as I would do on a multiple choice. So I want to see if the left-hand limit is equal to the right-hand limit. That's really what I'm going to see. So if I'm doing the left-hand limit, remember I'm approaching one from the left, so the numbers would be less than. So this is my equation that I would do because it says x is less than 1. So if I do direct sub on him, the limit from the left, I'll just write the notation out, that's going to be equal to 5 because I'm going to plug in 2 times 1 plus 3, and that gave me 5. Now the limit from the right is going to be, of course, the limit as x approaches 1 from the right of f of x is going to be equal to, I'll scoot him over a little bit, is going to be equal to me plugging in 1 into 3 minus 1, and that gives me 2. So is the limit from the left equal to the limit from the right? You go, no. I got 5 and I got 2, so what do I write when the limit from the left does not equal the limit from the right? The limit does not exist. Now, again, let's do this quickly, shall we? Let's do it. I have that same equation. Now be careful. This says x approaches -2. Well, gosh, where is -2? -2 falls in this one equation. -2 is less than 1. So when I do the limit from the left and the limit from the right, I would just plug in to that one equation and I would get the same thing for both limits. So that limit does exist and I would get -1. When I go to this third example, they're actually asking me for that break. So that's at 2. So the limit from the left, this is what I would do on multiple choice. I'd plug in 2 and go, okay, that one's 5. So that top one's 5, the limit from the left. I plug in 2 to this one, 2 squared plus 1. That bottom one is 5. Limit from the left, limit from the right equals the same thing. And so that answer is 5. Now, question. What if this bottom inequality, instead of saying x is greater than or equal to, what if it just said greater than? Would my limit still exist? Think about that. Would that limit still be 5 or would I have to change it to does not exist? Well, I hope you said the answer was still 5. Because remember with limits, I'm not asking if the function is continuous at 2, I'm asking does the limit exist? And even if that was a greater than, my limit from the left would be 5, the limit from the right would be 5, thus the overall limit is equal to 2. It would be a graph of something like, again, don't look at the curves because those aren't right, but the idea, you have a hole, but remember with holes, the limit from the left, the limit from the right is still the same, and so that limit exists. Make sense? Pretty easy breezy. Let's look at the next one. Let's look at the properties of limits. Now, I have typed out the properties of limits. Here's the good news with properties. If you do what you think, what is logical, you'll probably get it right. So even without me talking, or even without me looking down below at the typed out limits, if I said, hey guys, you have some function where the limit as x approaches 4 is 6, and you have some function, a different function, where the limit as x approaches 4 is equal to 2. If I ask you to do the limit of f plus g, and you're like, well, if I were guessing, I would do what? You'd probably say, well, I'd add the limits together. And that's exactly what you would do. So 6 plus 2, super simple, and that gives you 8. If I ask you the limit as x approaches 4 of g over f, just be careful in the order that you go. You'd say, well, logically, if I were guessing, I would take the limit of g and divide it by the limit of f, and that's exactly what you get. And you would get 1/3. And then, what about this one? Well, it's kind of a multi-step one, but if I have 3 times f of x, let's just consider that. If I had 3 times f of x, you would look at f of x and say, well, if it had a limit of 6, if I multiply it by 3, it's going to have a limit of 18. And then I'm going to subtract the g of x, which is 2, and I would get that limit to be 16. So properties of limits is just so easy. Now let's look at this next one. What would be the limit as x approaches 4 of e to the pi? Well, good gosh, what kind of thing is e to the pi? That's just some weird number, okay? Because e is some number, 2.71. Pi is 3.14, so e to the pi is just some weird decimal. What is the limit of any constant value? So think of this as being a constant. Well, think about the graph of a constant. If I said graph y equals, let's just call a number 6 instead of some weird decimal, let's just say 6. You would have a graph all along at 6. So no matter what value I'm going toward xy's, wouldn't my limit always just be the constant? And so this limit is going to be e to the pi. So you've just done the properties. Again, these things are what you just did. Okay, I didn't do a power one, but I could have. But they all of these just kind of make sense. Now I do want to talk about number 7, because number 7, that one might not make sense to you, and I want to talk about it because AP loves this question. What happens if you have a limit of a composition? Remember, with a composition, you kind of work inside out, and so you have to understand that if I want the limit as x goes to c of f of g of x, remember that's a composition, not multiplication. What you have to know is that it's the limit of the inner function, and then you do f of that limit. So let's do an example. Let's look at these graphs, and this will make more sense when we do the example. So let's make this bigger here. Okay, so let's write it out first. It says here are some graphs of h and g. And those would be given. Again, you don't have their equations, but that's okay. You're going to use the graph. Find the following limits. Well, when you see that limit of a composition, I would suggest writing it out. Remember, it's the limit of the inner one. So it's the limit as x approaches -2 of g of x. When I find that, I'm going to do h of that limit. So let's do it in pieces here. Let's see. Let's just do this inner part. Let's go to the g graph, so make sure you're looking at the right graph. What is the limit as x approaches -2? And hopefully you're an expert on that, because that's what we did yesterday. Remember, you go limit from the left, limit from the right, or my fingers going to the same spot. Yes, this closed dot is irrelevant. That limit is 0. So I'm going to replace all of that with 0. Now, what is h of 0? Looking at the h graph, where is the closed dot, or does it have a closed dot at an x value of 0? And you go, yeah, I see it right here. So that limit would be equal to -1. Okay? So I want you to try to do the other two. So remember, I want you to just pause the video real quick and then unpause it when you have tried those on your own. All right, let's see. Let's write them out. The limit as x approaches -2 of h of x, I'm going to do that first, and then do g of that thing. And again, so I'm going to look at the correct graph. The limit as x approaches -2 on h of x. So I'm looking right here. I'm going the limit from the left and the limit from the right. I am headed to the same value, and that value is 4. So I get g of 4. So I go to my g graph. They didn't label it, but I can count and say 4. Yep, I'm going to go way up there, and that answer is 5. And last but not least, this guy. I would do g of the limit as x approaches 0 of h of x. Sorry, those parentheses are kind of ugly. So the limit as x approaches 0 of h of x is what? Uh-oh, I have a problem. That limit does not exist. So how can you find g of does not exist? Well, that does not exist. So there's actually a couple ways of getting does not exist. That's one where this limit, excuse me, does not exist. The other way to get does not exist is, let's say that this G graph didn't have this dot. And when I took the limit of this inner function, I ended up getting -2. And so I was trying to find G of -2, but there was no closed dot at this X value. Well, then that would be does not exist as well. So there are a couple ways of getting does not exist. So I don't want you to think that that's a wrong answer if you're getting that answer, because that certainly is a possibility. So that's what you'll be doing this evening, doing direct sub and using properties of limits. Good luck.